Good day, and in this video we're going to talk about chapter 36, which is wave optics. And some good news are that it's the same, we're going to do a lot of the same things we already discussed about sound. Like for instance this. Here, the simulation of the two sources, which we did with water, but also applies to sound and also applies to light. So when you have two sources, you're gonna have constructive interference regions, destructive interference regions, and so on. As you modify the frequency, for instance, here, well, as you can see, you get a lot of regions with constructive, destructive, constructive, destructive. This is the case with light. The frequency in light is super short. So you get a lot of maxima and minima here, right? In light, when you cannot see this pattern from the side. Instead, what you observe is you see a pattern like this. You need a screen. You put a screen like here on top, in front of the light source or the two light sources, and you see regions of brightness and darkness, which corresponds to constructive and destructive interference. The person who first saw this, his name is oh my God, wait a second. His name is Young. It's the same guy which found and worked with let me write it here. Remember when we talked about stress and strain of materials, and I told you you get something like this, like when you compress a balloon, and then you get the bulk modulus, which I told you is like the springiness of the gas inside the balloon as you apply pressure. Well, if you have a metal, even if it's a strong metal, if you apply a force, heavy force, a large force, the thing is going to behave as a spring. And in the elasticity, in its elastic region, this constant, the equivalent of the spring constant in stress and strain instead of force and elongation, it's called the modulus of elasticity, E, or it's also called the Young modulus. So it's the same guy that now Thomas Young that performed an experiment to see if light was a wave as Huygens described. Right. So we have Huygens proposing the ideas of wavelets and all that, but then that was just a mathematical idea, a great mathematical idea, by the way, because he was able to derive Snell's law. So what Thomas Young did, I want to put it here. Thomas Young did is, okay, let's try to have interference. We saw that with sound is easy. All you need is two speakers, and then you get your interference. But with light is a lot harder, because conditions for if you want interference, what do you need? You need a few things. Number one, you need a single frequency or a single wavelength. In light, this means a single color or monochromatic light. So light of the same color. Number two, you are going to need also something called coherence. And what this means is same delta phi. You don't want the phase between the two sources. Of course, you're going to need two sources. Actually, no, I'm going to put it here. Oops. I'm going to erase this. And I want to say you need coherence between sources. So coherence means the two sources have the same delta phi. the same phase difference. The phase difference can be any number, but it has to be constant, right? So with sound, this is not that hard to achieve. Single frequency, same speakers, same oscillator for both speakers, and the coherence can also be easily adjusted as long as the two speakers are in phase at all times. But with light, this is very hard, especially in 1800s, when 1801, when Young did this, there were no lasers, there were no spectral lamps. He only had candles, and a candle, well, is not monochromatic, and certainly if you take two candles, you won't get coherence between the two candles, right? So the way he fixed this is he took the candle, yes, but then he put a filter, right? Just some tinted glass, like the one tinted glass, like the ones they use in churches to do the nice vitrals there. And then what he, after the filter, he knew about Huygens. So what he did, first thing he did is he put a screen in which he put a little hole. Oh my God, I cannot do this with this thing. So he put a screen with a little hole. So let's forget about the filter for a moment. So you get your waves. Yeah, your waves. Here come the waves, right? Whatever. And then when the wave hits this little slit, if I show you how this looks from the side, this is just a little hole like this, okay? So this is very thin, super thin, like razor thin, actually. That's how he did it, with a little razor. So very thin, so you only have like one point, and that's your secondary wavelength source. So now you have this. And then he repeated this and now he put another screen with two slits now, right? Two slits. So again, but with a knife or razor, he did two little slits. And the whole point was, so he managed the monochromatic aspect of the light with the filter. But then with the two slits, he makes sure that when light comes out of these two slits, right, it interferes like so. But look, this point and this point belong to the same wavefront. So they are in phase. So no matter what, in this experiment, the light that comes here is always in phase because it belongs to the same wavefront, and it is the same wavefront because according to Huygens, this point is a source of secondary wavelets. And what he saw for the first time in history was interference. Bright fringes, dark fringes, right? Which proved that Huygens was right and that light indeed behaved as a wave. So experimental proof is the first time we had experimental proof that light was a wave. So just again, when the two waves travel and reach a point where the path difference is m plus 1/2 lambda, you get destructive interference. When the two rays, or the two beams, or the two waves travel a path where they travel and the path difference is m lambda, you get constructive interference. Same thing as before. Now, what I will construct is, I'm going to zoom in. So this is one slit. This is called the double slit experiment for this reason. Or Young's experiment. So you have two slits separated by a distance d. And then, listen, in reality, the slits are super close and the screen is very far at a distance L. So D is a lot smaller than L. And that makes the rays, you see the rays, they're traveling This is the screen here. So one ray goes like this to a certain point, and the other ray goes like this to the same point. This is ugly, but it's really hard for me to draw on this tablet. So one goes like that, the other one goes like this. They're nearly parallel. So when we zoom in, right, and I'm going to a point here somewhere on the screen, with respect to this optical axis, here is the optical axis, okay, which is, let's say, the horizontal axis. So with respect to this optical axis, one ray is going like that, and the other ray is also going like that, nearly parallel, almost the same angle. We're going to call it theta, okay? So by the time they arrive, right, you see, by the time they arrive, the path difference is this little delta r, right? Here, these two beams, that's the path difference here, this little chunk. And here, well, this is like a triangle. This is 90 degrees here. And here, the angle theta appears again. So you get this triangle, basically. 90 delta r. This is d, the hypotenuse. And the angle here is... So you see, sine of theta is opposite over hypotenuse. Or delta r is d sine theta. So based on what we just said here in the previous slide, right, we can say that d sine theta, which is delta r, is m lambda for constructive, and d sine theta is m plus 1/2 lambda for destructive. And these are super important equations, not only for this chapter, but for the rest of the semester. Okay, so what it does is gives you the directions right here. Now we know at what angles we have constructive interference and at what angles we have destructive interference. As we saw here, you see there is an angle here. At this angle, you have destructive. At this angle, you have destructive. At this angle, you have destructive. So now you can solve for the angle. You say theta is arc sine of m lambda over d. Remember that m can be any number, 0, 1, 2, etc. So you have a lot of angles. You have one angle for constructive for every value of m, and you have angles for destructive for every value of m. Right? So this is the main equation. Here, we can continue. So in the screen, where this is your two slits are here. I'm exaggerating the d, of course, right? So what you're gonna get on the other end, on the side of the screen, is a pattern of interference, constructive, destructive, constructive, destructive, constructive, d sine theta and lambda, right? So again, the angle is sine of m lambda over d. So if you put m equals 0, this is all for constructive, you're going to get 0 degrees. So at the center, this is m equals 0. This is the position where you get constructive interference when m is equal to 0. You put m equal 1, and then you're going to get this angle here. This is m equal 1. So this is going to be m equal 2. This is m equal minus 1, and m equal minus 2. And these are called the orders. So the 0th order bright fringe, the 1st order bright fringe, 2nd order bright fringe, and so on. Of course, if you do the same with the other equation, you're going to get, when you put m equals 0, you get this little value here. This is your 0th order dark fringe. 1st order dark fringe. This is also 0, or minus 0 if you want. Minus 1, and so on. So that's what this equation does. Gives you the angles at which you have constructive and destructive interference. The last thing you can do is, if you know this distance from the slits to the screen, for a given position, well, you have the angle, right? So you can find the y, the position y, from the optical axis to the position where you have constructive interference, right? So tangent of theta is y over L, right? Now, in most of the cases, theta is very small in most of these problems. So we can do the small angle approximation, in which sine of theta is very close to theta and is also very close to the tangent of theta. Listen, this is sine of theta, sine. This is tangent of theta, or something like that. And this is theta, right? A line. You see, for small angles, they're all the same, just a little line. I'm going to redo this one because I don't like it. Remember, it's like this. I cannot do it. And then like that. I'm going to do it the other way. That's tangent of theta, right? So it's also a line. So this equation, tangent of theta for small angles, becomes sine of theta is y over L, but sine of theta is m lambda over d from this equation. So with this equation, you can find the height of the bright fringes. There is one height for every value of m, and of course there is an equivalent equation for the dark fringes. We're going to do a problem. We're going to do a problem with this in class.